Okay, Assalamualaikum and welcome to another session of Electric Drive, EPO640 Electric Drive. So for this lecture, we will continue on our discussion on AC drive. So this will be part 3 of our AC drive lecture. So we will be discussing on voltage to frequency control, and also we will look into vector control. Okay, so let's start. Okay, so what is voltage to frequency induction motors? Okay, motor drives, and it's the most popular variable drive system that is currently being used by the industry. It requires power converters which can provide variable amplitude, variable frequency, and variable voltage supply. Okay, variable frequency voltage supply. So in terms of performance, they have a poor dynamic response, speed droops, and also speed droops are when connected to load. Okay, so you have slip problems there. And but the control requirements are very simple. So the starting point for this analysis, okay, we will look per phase, okay, per phase equivalent circuit. And if you remember the equivalent circuit, okay, so from the past lecture, okay, so you can see you have your Vs, okay, and your omega, okay, omega E. Okay, that is the omega electromagnetic field. Okay, so in order to operate with a good rotor efficiency, which is the speed of the rotor, in here we make it as omega R. Okay, so in order to operate with a good rotor speed, the slip must be kept small. Okay, and with variable frequency operation, and if you want to change the rotor speed, okay, so of course you must change the electromagnetic speed, okay, the magnetic field speed, okay, omega E, okay, and of course the power will be transferred to the rotor speed. Okay, and how to change the speed, okay, so of course we will want to change, we will variable variable the voltage instead of current, okay, in this case. So if we look at the flux to the MMF, okay, chart here, so you can see that you have this saturation point here. Okay, so if you consider your flux, that is the air gap flux level, okay, flux G. Okay, so flux is controlled by the MMF. Okay, so you can see the magnetized current of IM, and the saturation, ion saturation as IM is increased above its rated value. So a large increase in current, okay, will only give a small increase in flux. Okay, so only on this region. Okay, so above this region you can see that ion will get saturated, and an increase or decrease of MMF will only affect a small amount of flux. Okay, so so ideally, okay, so for torque, okay, so ideally we want to control the flux to be as large as possible. Okay, so as we increase flux beyond its rated value, the ion saturates. Okay, and a large increase in current gives only a small increase in flux. Okay, so we get a disproportionate increase in I power to 2R losses, okay, due to larger current, and we get harmonics in AC current cause causes extra I power to 2R losses, and also get extra losses in the hysteresis, ion hysteresis. So therefore we control the flux to be at its rated value. Okay. So the rated magnetizing current is usually much smaller than the rated rotor current, and this keeps the total stator current, so either IM or IR, low, and also the copper losses, okay, I power to 2R losses are low. Okay. And at flux level below the rated flux, more total stator current is required for a given torque, and therefore increasing the copper losses, okay, and reducing the maximum torque capability of the drive. So therefore, for most application, okay, it's desirable to operate at rated flux, okay, so that the iron losses and the copper losses are at minimum. Okay. And the current must therefore be controlled to be constant, okay, at all frequency. Okay, so noting this equation here, and what we do is we control the voltage, okay, that will be proportional to the frequency, to the electromagnetic speed. Okay, so at high value of voltage, okay, and speed, electromagnetic speed or the frequency, so the voltage drop across the stator resistance and the stator leakage inductance is very small compared to Vm. So therefore we can say that the Vm is more likely similar to Vs. Okay, so because we are ignoring the leakage inductance. So Vs is controlled to be proportional to the frequency. Okay. So for Vf control, the applied voltage is proportional to frequency, and the above rated frequency Vs is held at its rated value. So it will result in the field weakening. Okay. And if you look at this, the graph here. Okay, so you have a condition, okay, so where Vs, the relationship between Vs and Vn. Okay, so of course you have this losses, VRL here, and in low values of Vm, okay, during low speed and frequency, so this value will be very significant. Okay, VRL will be very significant. So so some additional boost, okay, so Vs has to be boosted to maintain a good voltage to frequency ratio. Okay, and we can see here in the graph here, so this value is stated here. Okay, the boost is here, and after the value is kept low, so you can see that the increase of the stator to frequency here, you can see a linear, okay, linear proportional here, and when it reaches the rated voltage or the base speed, so you have this voltage will be constant. Okay, so another example that another example here, you have your torque to speed, okay, graph here. So you can see, for example, the motor characteristic. Okay, so if we apply a 25 hertz with 208 voltage ratio, okay, that is represented by the line in the green line here, and you have the 50 hertz to 450 volt, okay, that is represented by the red line here. Okay, so you can see the ratio here, okay, the ratio, and also you can see that a good linear region here, okay, within the speed here. Okay, so for example, for a 25 hertz 208 voltage ratio. So it's a good ratio for a 1500 RPM speed. Okay. So a variable speed drive, it only operates in the linear region. Okay. And you can see the of course the torque. Okay. The torque region. Okay. So if you have some slip here, okay, less than maybe 1480, so you can achieve higher torque. Okay. So yeah, you have the torque to speed characteristic, which the ideal condition will be during this region. Okay. So for example, in this example here, and if you look at a full what you call it, percentage, so if you are driving for let's say 0.1% of the speed, okay, of the rated speed, 0.75, so you have different you have your different hertz to voltage ratio. Okay. So the variable speed drive only operates on the linear region here. Okay, the linear region. And if we control the voltage, okay, to be proportional to frequency, so then we have a constant flux operation at most speeds and a series of torque speed curves where each line represents a different applied frequency. Okay, so you can see of course the positive and also negative. So negative is where is generating. And this can be developed, okay, by open loop. Okay, open loop voltage to frequency control, where the frequency, okay, and the voltage is applied to the variable frequency supply here. Okay, the power electronics part of the controller, and it will inject the appropriate frequency and voltage to the induction motor. Okay, so we can use the fact that the slip is small at rated torque. Okay, and for this simple open loop VF control, no speed feedback is required. Okay, but you have a slow dynamic response. Okay, and we have to include a rate of change limiter for the speed to prevent the slip increasing beyond its rated value. Okay, so of course, if you have high slip, okay, if you look at the chart back there, okay, chart previously, high slip will cause okay, inrush current, overcurrent. And based on the steady state equivalent circuit, it does not take dynamic response of real motor into account. And the speed drops by a small amount with the load. Okay. And another way to prevent this is by slip compensation. So for the VF drive, V2F drive. So incorporates a speed measurement. Okay, you have sensors. Okay, speed measurements and feedback. Okay, works on the principle that the torque is proportional to slip frequency, and the derivation of this scheme is based on a steady state analysis, which is not valid under rapidly changing conditions, and the dynamic performance is very poor. Okay, so more complex control schemes based on a full transient representations, okay, have been developed, and these are known as vector control, which we will discuss later in this lecture. And it achieves a better performance, okay, than V2F. So okay, here you have a slip compensation for V2F drive. So basically you have your this will be the V2F, okay, open loop, and this will be the closed loop system. Okay, you have a PI controller in order to dictate the value of the frequency, okay, together with a P controller, okay, the controller to dictate the value of the frequency and the voltage, okay. And here you have your sensor to detect the speed for the correction. And this will be linked to the VVF supply, okay, variable voltage, variable frequency supply. That is the power electronics part of the drive, okay. So the green box here. So basically it's a rectifier, and this is a converter, rectifier with the inverter before connected to the motor, okay. So for this you can use PWM, okay, to create your variable AC voltage, okay. So for this system you have a DC link here to connect, okay. High frequency switching, okay, depending on the output power, and to verify the duty cycle, okay. And it uses the diode to create a DC link from the AC main, okay. So the input will be AC that will be converted into DC, and will be linked within the DC link into the inverter. So the command switch for SA and SB using PWM, okay. So here, if you consider only one leg, okay, so you have your operation, okay, for the MOSFET, okay, for the switches SA and SB, okay. And yeah, you've been this will use the PWM, okay, method, And when the machine is motoring, the phase current drawn is roughly in phase with the phase voltage. So yeah, when D1 or D2 or D1 is conducting current flows to the DC link capacitor, so no current can flow into the diode bridge, okay. So this is a one-way drive method, So the IGBT is the switch, SA, SP, okay, using IGBT, okay. So it requires a logic signal, a control signal, okay, in order to turn on or turn off. And so the gate drivers it will amplify the logic signal, okay, and switch the IGBTs, okay. And it needs to create a pulse train for each IGBT to tell it when to switch on and off, okay, using PWM, okay. And pulses occur at fixed switch frequency, but the pulse width need to be changed in order to change the speed. And PWM creates the pulses based on the desired amplitude and frequency, okay. So I think you are very aware on this PWM, okay. So you have your modulation, okay, modulation wave, and your carrier waveform that is mixed together to is compared with the PWM output, and the relationship between the amplitude and the modulation wave, okay, you can see in this figure here, okay. So when it exits the comparator, you'll see this okay, this is shown in this figure, So yeah, a typical spectrum, okay, of the this is when we apply FFT, okay, to the spectrum, to the carrier, to the voltage, So if you look at the value of the fundamental, the percentage of the this is the maybe the second harmonic, second carrier and the sidebands, okay, first the fundamental with the third harmonics, okay, so you can see that it's not it's quite not good voltage waveform here. Okay, so yeah, this can be filtered. Okay, we can improve this waveform by applying filters. Okay, and yeah, how does the motor works with such an awful voltage waveform? So this will be the example of the distorted sinusoidal current, motor current. But then the motor is a inductive. Okay, so its impedance at high frequency is high, and therefore the voltage components associated with FC gives rise to much less current than the fundamental. Okay, so yeah, the machine reacts predominantly to the fundamental components. Okay, so although you have all these harmonics, okay, containments in your voltage, but then due to its load, that is highly inductive. Okay, so inductive load, they only react to fundamental waveforms, and okay, so to reverse the speed in the motoring mode, okay, you can simply change the phase order. Okay, and normally phase leads phase B, okay, phase C, okay, and to reverse the machine, you can make phase A lead phase C, okay, and so on, okay, and that's one way to reverse the speed. Okay, and if the machine is driven above the frequency, okay, by the load, so the machine will regenerate and the phase current will be roughly 180 degrees out of the phase with the phase voltage, and there will be a large transfer of energy to the capacitor. Okay, and VDC will charge up, so it's something that is dangerous, and something must be done to prevent VDC, okay, from rising uncontrollably. Okay, so in this case, you can see here, you can see the change of the speed will actually suffice. Okay, the voltage will increase in your DC link. Okay, so this can explode. So what they do is they put in a dynamic braking resistor, okay, before connecting to the in parallel with the capacitor. So when the regenerative current, okay, that causes the DC link capacitor voltage to rise. Okay, so there will be a system, a power electronic switch is activated, which will discharge, okay, the excessive the power to the large resistor, and it will act as a energy dump. Okay, and it will dissipate it in the resistor as heat. Okay, so this is one device, okay, for regenerative braking. So in order to control the excessive energy, okay, and also if it's a 4-quadrant drive, it will have this regenerative. It will supply back to the grid. Okay. So the induction motor is the most popular. Okay, conclusion for your V2F drive. So the induction motor is the most popular motor for variable speed application. The motor is rugged. Okay, it's spark free and requires little maintenance. And V2F is simple to commission, simple to install, simple to commission, and its poor dynamic performance and close speed holding are acceptable, okay, for most application, for many application. And nowadays the Igbt inverters are relatively cheap and it's easy to use. Okay, and the power can go up to 100 kilowatt. Okay, but you have a disadvantage such as the diode bridge draws poor supply current, and its high dynamic response require the added complexity of a vector control. Okay, so for more complicated application, they will use vector control. So you can see simple application for V2F, for example, for industrial fan, okay, for compressors and for pumping. Okay. So for high performance drives, okay, so what is the definition? Okay, high performance drive. So a motor drive in which the motor torque obeys a torque demand within a few milliseconds. Okay, so in some application, you need the agility of the motor to obey certain torque, okay, torque demand. Okay, so induction motor driven by a V2F PWM converter is not a torque control drive. Okay, it's not suitable for this torque demand that can obey few milliseconds. Okay, and why? Okay, so you can see at the following. Okay, so the drive, for example, at the following torque control drives. So you can see, for example, drive designed to go from one speed to another. Okay, so from one position to another as quickly as possible. So this is for industry that uses speed position servo drives. Okay, drive. Okay, so they need a servo drive. Okay, servo drive. Okay, in order to execute this. So these are, okay, you can see other examples here. So these are what you call, okay, servo drives is what we call high performance drives. Okay, so example of this servo drives. Okay, okay, you have for machine tooling. Okay, lacing machines. You have all these modern lacing machines. Okay, positioning. Speed and positioning servos. Okay, for robotic arms. Okay, traction drives. Okay, you have for railways. Okay, you have for cranes, lifts. Okay, object positioning, tracking. All this needs a high performance drive. Okay, so traditionally all torque control drives has been a DC machine. Okay, and DC machine torque can be controlled directly and effectively. And usually, traditionally, AC machines are steady state machines. And now, having this type of drive, servo drive, you have AC vector control induction motor drives will be replacing DC drive. Okay, for all high performance application. Okay, so this is because induction motor are more simpler, is less expensive, is easier to manufacture. Okay, induction motor has low maintenance. Okay, capable of fast torque response. Okay, capable of faster speed response due to low rotor inertia design. And the cost of an AC PWM power converter is more than the AC to DC tri-listor converter. Okay, but now since you have this semiconductor, okay, and silicon products, okay, the advancement in this area and in this manufacturing makes the cost cheaper. Okay, so and the cost is recovered through cheaper machines, maintenance, and high performance. Okay, and so vector drives need much higher okay, microprocessors power, okay, microprocessor power. But now it's not a problem. Okay, you can see very okay, microprocessors are now it's very fast. Okay, you have now you have AMD with AMD Ryzen, you have Intel i9. Okay, so microprocessor power is not an issue. And it's so cheap. Okay, so having that the vector control drives will be replacing the V2F PWM drives, and it can run machines more efficiently. Okay, and at low powers. Okay, so most of the manufacturer offers a universal drive. Okay, and for extra costs in one of the extra current transducer, okay, it can also be overcome. Okay, and what is the main competition for vector control IM? So now you have permanent magnet machines that have better torque density. You have permanent magnet drives. Okay, permanent magnet. Of course, permanent magnet. You have problem with magnets. Okay, magnet is you need to mine rare earth. That is something that is very valuable. Okay, and also you have now you have switch reluctance motor that has some niche application. Okay, so let's look into vector. So before we go for vector control, we will look into how magnetic field is produced. Yeah, and by the way, I will post a very interesting video on the magnetic field. Okay, on how magnetic field is produced. You can see the relationship between the voltage, the current, and also the MMF. The MMF, sorry, the voltage, the MMF, and the flux. Okay, okay. So you can see how in three-phase the value of voltage, the value of MMF, and the value of flux, okay, will recreate the speed of the magnetic field. Okay, so in this example, you have a three-phase example here. Okay, so you have for phase A, phase B, and phase C, which is 60%, 60% indifference, and this will affect the magnetic, okay, space magnetic. So I and okay, the current MMF and the flux, of course, it will vary within time. So the current, since the source is a sinusoidal source, so you have current peak, okay, and you have the negative peak, and so on. So of course, I will definitely will produce the flux, okay, and it will vary within time. Okay, later on we'll see. So in the steady state, the current and the flux are the AC quantities. Okay, and of course, if the current is supplied in sinusoidal, the flux will also produce in sinusoidal. Okay, so you can see the magnitude. Okay, so starting from okay, low, middle, high, middle, low. So it's sinusoidal, sinusoidal condition here. So this is during negative. Okay, negative. And also you have the same case for B and C. Okay, so it's three phase. You have phase A, phase B, and phase C. So here is an example here. Okay, so I think it's better if you look at the video that I will post with you. Okay, on the space vector for each red, yellow, and blue phase. Okay. So then if you look at here, so it is easy to imagine the main flux vector rotating around the air gap of the machine with an associated magnitude, frequency, and angle. and it is more difficult to imagine, but the applied three-phase voltage and the resulting stator current can also be considered as vectors rotating with angular velocity. Okay, so angular velocity, okay, omega E, and this will be interpreted also for frequency. Okay, so in the video that you will be looking after this, so you can see the rotating field. Okay, so that will be that will be what we call the speed. So the speed of the rotating field is the electromagnetic speed. Okay. So note that the steady state value of the voltage, current, and the flux are constant values. Okay, and you can see for most condition, okay, so the changing of voltage, current, and the vector will of course result in the rotating field. Okay, so the vectors can be redefined in a rotating frame of a reference, and this rotating frame of reference is commonly known as the DQ frame. Okay, and the d-axis is usually aligned to the flux vector, and we will make the q-axis led by 90 degrees. So looking at the quantities in our motor, we can define flux, voltage, and current in this dq axis frame of references. Okay. And we have defined, okay, a current that is in phase with the flux vector to a current that is orthogonal to it. Okay, so that this means that the ID is purely flux producing, and IQ does not influence the flux. So IQ must therefore be purely torque producing. Okay, you have ID and IQ, and therefore we have defined elements of the stator current which may allow us to independently control the flux and torque in the induction motor. So just like how we control for a separately excited DC motor, okay, ID and IQ. And ID is normally kept constant at a value equal to the magnetizing current of the motor, and it is reduced at higher speeds for field weakening. Okay. And if we look at the control, okay, so you have your transformation DQ to okay, to phases, phase A, phase B, okay, red, yellow, blue, or ABC transformation. So then it will convert into your PWM and inverter. Okay, so this will be the speed control. Okay, speed control. And what do you then okay, is used to calculate the ID and IQ. Okay, so you can read further here, and thus calculating the A, B, and C, or red, yellow, blue. Okay, so yeah, so this will be known as the vector control. Okay, indirect vector control. Indirect vector control. So okay, field orientation, you can read further within the reference that is posted in this on the reference page. So in conclusion, vector control AC drive uses mathematical manipulations to convert three-phase AC quantities to DQ quantities which are in direct current DC. So that in condition if it's in a steady state. Okay. So torque is changed in response to speed change. Okay, and IQ reference is therefore usually the output of the speed controller. And fast controllers are used, okay, to maintain ID and IQ at their demand values. So VD and VQ is directly influenced to ID and IQ. And the machine, when correctly field oriented, is controlled in exactly the same way as a separately excited DC motor. and we can use a nested control loop similar to a DC machine to create a high performance AC motor drive. So to design inner current loops, okay, you have to have a high bandwidth. Okay, D and Q loops have the same control parameters, and to design the outer speed controller, okay, so flux controller will be required. Okay, so there. So for that, thank you, and have a nice day.